Hello students, welcome to Inside Physics. Today we are going to discuss about Bragg's law in X-ray diffraction. We all know diffraction is a process shown by light when it is encountered by an obstacle in its path. So whenever it finds an obstacle, it just changes its direction. That means it changes its rectilinear path and it diffracts from the edges of the obstacle. That is called diffraction of light, and we have discussed it in earlier classes. So here X-rays, which are powerful electromagnetic waves which are electrically neutral, are also being diffracted when they are incident on some crystals. So that is called X-ray diffraction. And Bragg, two scientists called Bragg and Bragg. So H. Bragg and Bragg, two scientists in 1912, they have found out a good relation between the diffraction of X-rays. That means the relation says something about the angle of scattered beam and wavelength of X-rays and the interplanar distance. This is the distance between two successive planes, which is denoted by d. So this Bragg, in his observations while doing some diffraction experiments on crystals with X-rays, they found out a relation between the angle of the scattered beam, that is also called angle of incidence or scattering angle, and wavelength of X-rays represented by lambda, this is theta. So a relation between these three, which gives a condition which tells us that the X-rays diffracted are being interfering constructively or destructively. That means if the interfering diffracted X-rays are being satisfied by this condition, then it will form a bright spot as a diffraction pattern. Here we can say some planes in the crystal are called crystallographic planes. Crystallographic planes, that means in the crystal structure we have taken some plane on which the lattice points are arranged in a systematic way. So the lattice point is nothing but where the atom is residing at, so that point is called a lattice site or lattice point. So crystallographic planes are lattice planes or which the atomic arrangement is in a systematic way, and the plane which contains the systematic arrangement of atoms is called crystallographic planes. Here in these diagrams I am showing two planes here which are at some distance apart. This is the first plane, this is the second plane, and these planes are, you can imagine, they are perpendicular to this board. So when you consider the atomic arrangement in the systematic order, generally in crystals, why they are called crystals, the solid material, because of the regular pattern of atomic arrangement, they have a fixed shape, unlike liquids and gases. So in this way we can define a crystallographic plane, and by these planes are called cleavage planes by Bragg. Why they are called cleavage planes means, see, they are having some space, some cleavage between them. The spacing, interplanar spacing, it will be very small, of the order of something like a wavelength of the incident light. So this cleavage is the reason for the path difference of the reflected wave and incident wave. So these cleavage planes are also famously known as Bragg planes. Okay, so these planes are actually diffracting the incident rays because the atoms are being hit by the incident X-rays, and the atoms as lattice points are the cause for its diffraction. So here see, when it is considered as a reflection, the diffraction in Bragg's treatment is considered as reflection. Why? Because see, when it is being incident and it is reflected back into the same medium, even though it is a diffraction pattern, we can also consider it as it a reflection. So here in this Bragg treatment and finding the relation for the this reflection, we can treat the diffraction and reflection terms in the same way. Diffraction and reflection, we can treat these two terms as interchangeable in the Bragg's explanation. So why? Because see, they are being reflected because of the atom in the lattice planes. So when the incident wave is passing through between the spacing of the atoms, it will not be diffracted. So the incident ray is being diffracted or reflected partially. That is the reason why we take this incident is only a partial reflection. Okay, now there are some statements made on the observations made on the X-ray diffraction in crystals. So these planes are considered as semi-transparent mirrors in this Bragg's treatment. Semi-transparent mirrors. Why? Because in mirror what happens? Reflection happens in a mirror. So semi-transparent, some of the light, not all the light, is being reflected. So if it is a mirror, so where there is most of the light is being reflected, that is called a perfect mirror. But these planes are actually considered as a semi-transparent mirrors. Okay. So here the lattice points of the planes are the actual cause for the reflection. So in this way, some of the statements he has made is the semi-transparent mirror and lattice points of the planes are the reason for diffraction. So whenever the interplanar spacing is of the order of, see, interplanar spacing is nothing but we can consider it as d. So whenever they are having some incidence and reflection, they will be having some path difference, right? So whenever an incident light is incident on a medium and it is being reflected, the incident light and reflected light will be having a path difference because we consider two incident lights at two lattice points. They are incidenting at 2 points, so they must have a path difference. So if the path difference of the two reflected waves is in accordance with the interference pattern, if it is integral multiples of the wavelength of the incident light, then the path difference is causing the constructive interference pattern. Path difference, if the path difference is equal to integral multiples of lambda, it will be causing the constructive interference, thereby the reflection pattern forms the spots, bright spots. Okay, so these are some of the observations made by the Bragg in while doing the X-ray experiments on crystals. So we will go to the actual treatment to find the Bragg's relation. Here we have given two diagrams where this is the pattern where there are two atoms arranged one besides the other. So the reflection is happening from the same plane, but the incident lights, if you call them as incident light 1 and 2, so they can name it as A, this as B, this as C, this is D, this incident light is E, okay, and this is F, this is C. A, B, I should name it as B here. A, B, C, D, E, F. Okay. So this is a reflection pattern where the reflection is happening from the same plane and with the two lattice sides arranged side by side. So when it should form a, if it is having some constructive interference, means the path difference must be same. The path difference must be equal. What is the path difference here? See, this BH is the path difference and GE is the path difference. So BH, that BH must be equal to GE. So when this path difference is equal, then we can say that the angle of incidence theta is equal to theta dash, where because of the reflection rules we can consider theta is equal to theta dash. So in this case, this is the perpendicular drawn, HE is the perpendicular drawn to the light incident X-rays AB, and GB is the perpendicular drawn to the incident X-ray light EF. Okay, so when you consider theta is equal to theta dash, then this is equal to the reflecting angle. The path difference must be equal to form a constructive pattern. Constructive interference gives us the visibility, right? If it is forming a dark spot because of the destructive interference, we cannot have the visibility, we cannot record the reflection pattern. If it is only constructively interfering, the intensity of the light will be high, so we can record the pattern and we can understand the crystal structure because of the incident pattern. So in this way we will move to the next figure. Here in the bottom we will consider the actual Bragg's law from this second figure. So this is the incident ray AB, incident X-ray. We should give the direction of incidence. This is the reflection after hitting the lattice sides. So here the difference is the reflection is taking place between the two planes when the incident rays are incidenting on two different planes. Here in this case it is incidenting on the same plane. So when actually if we say the interplanar distance is d, small d is considered as small d, so this is incident on the first plane, MN is the first plane, PQ is the second plane, and if you consider the second X-ray DE, it is incidenting on the second plane on the lattice point where it is exactly above the lattice point on the first plane. So this is the systematic arrangement of the lattice points where each atom is placed in a regular pattern. So if you observe some angles in this diagram, so we will understand what are the angles and what are the perpendiculars drawn here. If you understand BG is a perpendicular drawn to the incident X-ray AB, and again BH is the perpendicular drawn to the incident reflected ray BC. Okay, so from this picture what we can write is angle ABG. Just we will be observing and we will be having what are the actual angles. So we will study the pattern and then we will go to the derivation of the Bragg's law. Angle ABG, if it is a perpendicular to AB, this must be of the angle 90 degrees. So what is the other angle? MBE. This is the perpendicular distance, interplanar distance BE between the two successive planes. So we can say angle MBE is equal to also 90 degrees. So as per the reflection rules, if this is the theta incident angle, if this is the angle of reflection, both are same according to rules of reflection. So we can say that ABM, angle ABM is equal to angle CBN. That we can understand easily. So next, what is this angle alpha? So if this is theta, this is also theta. If this is theta, this is also theta as per the rules of the straight lines. Then alpha plus theta from this diagram is obviously 90 degrees. We can write angle MBE is equal to 90 degrees and angle GBE, angle GBE is equal to theta. So here MBE is equal to 90, that means alpha plus theta. So this can be written as alpha plus what is theta? GBE. This is a description what I am giving to understand the angles in this particular incident reflection pattern. So if this is alpha, this is also alpha. If this is theta, this is also theta, and this is theta, and this is also theta. You can understand that the incident and reflection pattern and how the angles are being taken. So the main concept here is to go ahead. First of all, what we need to understand, what is the path difference between these two rays, the path difference between these two reflection patterns, the first reflection and the second reflection. The first ray is incident at B and reflected, the second ray is incident at E and reflected. So there must be a path difference because they are being reflected from different lattice planes. What is the path difference? If you observe GE and EH, so this is GE, this is EH. So the path difference will be, so why we need path difference? If we know the path difference, we can say that these reflected, these two rays, whether they are interfering constructively or destructively, that we can say if you know the path difference. The path difference from this diagram we can write GE plus EH. Okay, this is the path difference. So we should understand from this diagram what is sine theta. Try to understand from triangle GBE what is sine theta. So BG by BE. BG, that means see opposite side, see this sine theta opposite side by hypotenuse. From this triangle GBE we can take sine theta is equal to opposite side GE by hypotenuse. Okay, GE by hypotenuse means BE. So we can write GE by D. What is this distance? BE is nothing but interplanar distance D. In the same way, from the triangle EBH, we can say Sin theta is equal to opposite side EH by hypotenuse, EH by hypotenuse BE. That means it is EH by D. Equation 1, equation 2. Just observe the equations. So from this we can write, from equation 1 we can write G is equal to D sin theta, and EH is also equal to D sin theta. Okay, what we want to know, GE plus EH, sorry, this is EH, GE plus EH. So what is GE plus EH? Is equal to 2D sin theta. This is the path difference, GE plus EH. Okay, delta L, the path difference will be GE plus EH is equal to 2D sin theta. We know if the path difference of two reflected rays, here are the X-rays we have taken, then if it is integral multiples of the integer, the integral multiples of the wavelength of the X-rays, then we can say from this, these two rays will be interfering constructively and they will be giving a bright spot. So that will be recorded on a photographic plate. Because of the bright spot, we will be having high intensity. So the pattern being recorded, the intensity of light is being recorded on a plate. By that analysis on the photographic plate, we can understand what the crystal structure will be. So here the Bragg's condition, this is called Bragg's law. We can write the Bragg's condition as 2D sin theta is equal to m lambda, where m is equal to 1, 2, 3 and so on. Whenever the wavelength of incident light or incident ray is multiplied with these integers, that means here the interference pattern will be a constructive pattern. Okay, so see, if we consider as an example, if you take the plane 1, 0, 0, that means the reflection is being done from the first plane 1. See, it is the plane on which we take as on the x-axis. So it is considered as a plane, and if the incident and the reflection is considered with this plane, we can say that for m is equal to 1, there will be a path difference of lambda. Okay, so if the second order, that means if it is incidenting from the second plane, well, then if for m is equal to 2, there will be a path difference of 2 lambda. Okay, m is the order of reflection. You can say m is the order of reflection. So in this way we can consider the Bragg condition to determine the reflection pattern. So if any X-rays are incidenting on the crystal, they are being reflected and the reflection pattern is being recorded. If they satisfy the Bragg's condition, they will be forming the bright spot with some high intensity, so that we can record the observations and study the crystal structure. So from this, if you want to know the reflecting angle of reflection, the scatter beam will be reflecting with some angle, that is called angle of scattering also. We may interchange the terms like this. This is the Bragg condition, and we may take this 2D to the right side. So theta is written as sine inverse of m lambda by 2D. Okay, for if the order of the reflection is fixed and the lambda wavelength of the light incident rays are also constant, if m and lambda are constant, so the angle of reflection is dependent on the interplanar spacing. That means the angle of reflection is dependent on d. Theta is dependent on d if m and lambda are constant. Theta is dependent on d if m and lambda are constant. So this is how we can describe Bragg's law of X-ray diffraction. This is a good observation made by Bragg, because so for crystal structure analysis, the reflection pattern, so diffraction and reflection almost considered as of the same meaning in this treatment. Okay, this is what about in this session. We can move to the next session with some other topic.